So now in this video I thought it would be fun to look at a time delay circuit using a transistor and capacitors, and our load will be an LED lit with a resistor. So the power is already on. I have a switch up here. The top of the switch, both sides are always connected to each other along the top. It's separated top to bottom. Both sides of the bottom are always connected. That's one thing to remember with these tactile push button switches, at least all the ones I have. The transistor we're going to use is the 2N2222. Looking at the flat side there, left pin is the emitter, middle pin is the base, and right pin is the collector. So if we turn it this way, now the top pin is the collector, the middle pin is the base, and the bottom pin down there is the emitter. So we're going to just plug it in right there to this jumper. So the emitter needs to be towards the more positive side of the power supply, collector towards the more positive side of the power supply, and the base, we will give it a control which is going to be more positive than the emitter, and so we will control the current going through there, which will control the current. We'll control the current going from base to emitter, which will control the current going from collector to emitter. So we're going to add a load. We're going to take the LED. As I said, the collector will be more positive than the emitter, so we're going to put the cathode, short lead of the LED, to the collector. Long lead, the anode, heading towards the more positive side of the circuit, is up one row. And then we're going to use a 220 ohm resistor. Exact value of the resistor does not really matter. Just higher value resistors will make the LED a little bit more dim at any given point. But this is a good about minimum resistance. It'd be better to use more than less, because we're getting a little bit close to its wattage limits. So in any case, we have over here the switch. We're going to put in a 47 microfarad capacitor to the switch there, and we're going to leave one spot right there. So when we close the switch, even though it's on the other side of the switch, we'll still get a positive signal over here to charge the capacitor. That's the main takeaway. So I'm going to grab a 10,000 ohm, 10 kilo ohm resistor. We're going to go to the middle pin of the transistor right there from the capacitor. And you can see the transistor is off. The power is on right now, but the transistor is off. So I'm going to hit the button. This is a 10,000 ohm resistor. And you can see now we turn it on, and normally when you turn off the switch, the load turns off. But the switch, actually, when we're holding it, it is powering. It's sending current through the resistor to the base, to the emitter, and to ground, which is allowing a lot more current to go from collector to emitter in the hundreds of times. But of course, it will only let through whatever current the resistor and the LED will let through when the transistor is saturated, when it's conducting fully, which it is right now. And then when I let go, there's still a voltage and charge on the capacitor, so it discharges through the resistor, and as the voltage drops, less current will flow, and ultimately the load dims. So that is with a 10,000 ohm resistor. You can see how fast that's going. Let's take a voltage reading, and we're going to look at the voltage across the transistor. And so I'll move the LED up. So we're just going to measure across the transistor. I'm going to hold down the switch, and that's probably about the voltage we'll have across it, because it doesn't conduct perfectly. A piece of wire would have no voltage across it. So it's got a tiny bit of what we could call resistance, and it's not conducting perfectly, but pretty well. You can see there's barely any voltage across it, whereas if we go across the LED, you can see there's voltage across it, and the rest of the voltage is across the resistor, which is setting the current. And actually, let's get back to the transistor. So I'm holding it down. Now you can see it's saturated. When I release the button, pretty quickly it's not conducting perfectly, and it's blocking more and more voltage. It's letting less current go through for the most part. And so in any case, we can extend the time. We'll take out the 10 kilo ohm resistor and put in a 33 kilo ohm resistor, 3,300. So this will put 1/3 of the current through the base to emitter when we hold down the switch, and so it looks like it's not conducting completely saturated, but pretty close. It's not blocking much voltage. But I release the switch. There you can see it's taking longer for the voltage buildup. So probably about 3 times as long, because it's probably going to take 3 times as long for the capacitor to discharge. So one thing we can do, if we really want to extend the time, take this out, this capacitor, and 47 microfarad, and replace it with a 470 microfarad capacitor. So that's a lot larger capacitance, and I already discharged it, so it's fully discharged. But now you can see we have the voltage built up across there, and we hit the button really briefly, and you can see that it's barely blocking any voltage. So the load is pretty much fully on right now, and so whatever point you want to call it, not saturated anymore, it's pretty much fully conducting. But now you can see it's rapidly blocking more and more voltage. The LED is going to get more and more dim because the LED and the transistor are taking away voltage. At this point, they're both taking away almost 4 volts away from the resistor, and whatever voltage is left to go across the resistor will set the current based on its resistance. So that's still a fairly slow process because it's a much larger resistor. So we can go back to the smaller, the 10 kilo ohm resistor right there, and it will speed things up quite a bit. But there, even as you can see there, it's taken some time. So if you want, and there you can see we have an even better less voltage across the transistor. It's conducting even better, which makes sense. It has more current going through the base, and that's probably as good as it will conduct. But there you can see it's still taking time to build up the voltage that is blocking. So you can use a capacitor and a resistor for the RC time constant. That's whenever you have a capacitor charging or discharging through a resistor, it will take a certain amount of time to either charge or discharge from where you're at to 60% of what voltage difference is less. And you multiply the capacitance in farads times the resistance in ohms, and that will give you the time constant that it'll take to go about 63% from where you're at to that point, and then from your final destination, and then it'll keep stepping up. You'll get 64% closer, and then 64% closer, and 64% closer for each time constant. But in any case, hopefully that all made sense. This is a pretty educational circuit. You have the capacitor and the transistor working together. The capacitor setting the time, and then the transistor, it is just taking the current that's naturally flowing. It has a voltage drop that affects the discharge a little bit, but for the most part it's looking at the time it takes for that current to go down, and then applying that to a load. And so as long as the current's high enough, it can keep a load fully powered, current from the capacitor. But as the current goes down, then it limits the current to the load, and the load fades off, which may be something you want at some point. So hopefully you enjoyed the circuit. Thanks for watching. I'll see you in the next one.